Hey guys, I just finished taking a big old shit, and while I was doing so, I thought of a good topic that I'd like to discuss. That is the gabapentinoids and the difference between gabapentinoids and actual GABA receptor agonists and ligands. I think there's a lot of confusion, rightfully so. Because gabapentinoids, people tend to equate the name with GABA, the endogenous ligand of the GABA receptors, and also with the GABA receptors themselves. So I like to get into that. And all right, so first things first, I like to address the molecular differences between gabapentinoids and GABAr ligands. So here I have the three prototypical gabapentinoids. We have gabapentin, pregabalin, and phenibut. Now, the reason that they were named gabapentinoids is not because they have any activity at the GABA receptors, but it's because of their visual similarity to the endogenous amino acid GABA, or gamma aminobutyric acid. So if you have gabapentin, it has many of the same qualities as GABA, gamma aminobutyric acid. It closely resembles the naturally occurring amino acid GABA. You can see the structure of GABA in the structure of gabapentin. You have the gamma aminobutyric acid group, and gabapentin has that same skeletal structure with a saturated cyclohexane ring attached at this position. That similarity is why they're called gabapentinoids. They do not bind to the GABA receptors. GABA does not bind to the gabapentinoid receptors or to the alpha-2 delta receptors. But coincidentally, they look very similar, which is why they're named as such. The gabapentinoids bind to the alpha-2 delta subunit of certain voltage-dependent calcium channels, while GABA and other exogenous GABA receptor ligands bind to the GABA receptors, the GABA A and GABA B receptors. So these are some examples of GABA receptor ligands. We have alprazolam, a representative for the benzodiazepine class of molecules, which all bind to the benzodiazepine site on the GABA receptor. And then we have zolpidem, which here represents the class of Z drugs or non-benzodiazepines that also bind to the benzodiazepine site, but are called non-benzodiazepines because they lack the benzodiazepine ring structure. They have they're chemically distinct from most benzodiazepines. And then we have phenobarbital, which is a representative of barbiturates, and which also interact with the GABA receptors. And these all interact in a similar mechanism, which I'll address later. So then we have the endogenous ligands of both the alpha-2 delta subunit containing VDCCs as well as the GABA receptors. So the endogenous GABA receptor ligand is GABA, as mentioned before. And the endogenous alpha-2 delta ligands are L-leucine and L-isoleucine, both amino acids, and both ligands of the site that gabapentinoids bind to. So now that we got the molecular structure differences out of the way, I'd like to go into the receptors themselves. Starting on the left here is the GABA A receptor. Now, this is an ionotropic receptor. If you watch my video on NMDA receptors, it's a similar mechanism to the NMDA receptors. But while NMDA receptors are excitatory in nature, as in they increase the probability of the propagation of an action potential in a neuron firing, the GABA receptors, on the other hand, are inhibitory receptors, meaning that agonism at their orthosteric site will elicit an inhibitory response within the neuron. In the case of GABA A, that response might be, so there are two sites here. One is the orthosteric site, which is the site that the common site that endogenous ligands bind to. And then here, this kind of square shape, I drew to illustrate the allosteric site. And the allosteric site is a regulatory site. It's not, it doesn't directly activate the receptor. It's dependent on something else binding here, and then it modifies the action of this ligand. Or it changes the geometry of the receptor when it binds so that this binding site is more accessible by the ligand. So it either potentiates the response or stimulus, or it increases the chance that a ligand might bind to that site. So with the GABA receptor, let's say we have GABA, gamma aminobutyric acid, bound to the orthosteric site. And then we have alprazolam bound to the allosteric site, which is the benzodiazepine site, which is also what barbiturates and non-benzodiazepines bind to as well. The binding of the benzodiazepine here increases the activity of the GABA receptors as a whole. And what that means is, I mean, usually these are in a closed conformation when there's no GABA bound to them, but right now they're illustrated as open. So when the GABA binds here, it opens the receptor or the ion pore. This is a side view, and this is the cellular membrane here. This is the synaptic cleft, the extracellular space, and this is the intracellular neuron that's associated with this receptor. So from a top-down view, it might look like, something like that, where this is the top-down view. The receptor itself is comprised of multiple subunits, and within the middle is the channel pore in which the ions can transport through. So when it's closed, it forms a enclosed tight formation, so ions can't move through. And when you have something binding to a site or whatever, it opens up, and it's just easier to illustrate with a side view. So that's why I'm using that. But I thought I'd go into that just because I didn't really address that in the last video, and it might be a little confusing to some people. Back to the GABA receptor with the orthosteric ligand GABA bound and the allosteric ligand alprazolam bound. Outside of the cell is chloride anions, that is negatively charged ions. And when this opens, it allows those to be transported into the intracellular neuron. And what that does is it increases the polarization of the cell. So when a cell is hyperpolarized, that is that there's a large concentration of negative ions in it, as opposed to positive ones like potassium, it becomes much less likely to fire, because for a cell to fire, or for a neuron to fire, it requires a large influx and then efflux of cations, that is positively charged ions, and this reduces the chances that will happen. It increases the amount of cations that would need to enter the cell in order to elicit or to propagate an action potential and for the neuron to fire. So they're kind of like the inhibitory brother of the NMDA receptors. They work in very similar ways, except with differing effects. So next, I like to talk about the GABA-B receptor, which is also targeted by benzodiazepines. And interestingly enough, you might have noticed in the illustration of the gabapentinoids, we have phenibut right here, which is also partially enclosed within the GABA receptor ligands. And that's because phenibut uniquely has activity at the GABA receptor as well as activity at the gabapentinoid site on the alpha-2 delta receptors. And it acts as an agonist at GABA-B receptors. So GABA-B receptors are distinct from GABA-A receptors in that they are not ionotropic receptors, they are metabotropic, which means that instead of directly opening an ion channel, like in the case of GABA-A receptors, the GABA-B receptor is a G protein coupled receptor. So you have this G protein receptor here. It's a transmembrane receptor. It goes through the membrane. And when something binds to the site, the orthosteric site on it, like in this case, let's just say it's phenibut. It doesn't directly open a channel pore or anything. It doesn't increase it doesn't cause the influx of ions directly. Instead, what it does is it uses a secondary messenger within the cell. In the case of the GABA-B receptor, it uses PIP2 or phosphatidylinositol bisphosphate, which is a secondary messenger protein that is stimulated to interact with an ion channel that is adjacent to the G protein GABA-B receptor. So the binding to reiterate, the binding with phenibut causes the activation of PIP2, and that then interacts with the adjacent ionotropic receptor. In this case, it's usually a GERK, G protein coupled inward rectifying potassium channel. So you might be thinking, if GABA-B activates this GERK, and that's an inward rectifying potassium channel, you're going to have cat ions moving in because of that. And that might be counterintuitive because in my previous video, the NMDA receptors cause the influx of calcium, which increases the depolarization of the neuron and then increases the chance it'll fire. And it is a bit counterintuitive, but in the case of GABA-B receptors and their interactions with GERKs, it's more so of a stabilizing effect. The influx of potassium in this case serves to stabilize the membrane potential and return it to more of a baseline. And the inward rectifying part of GERK means that it primarily lets the ions in, preferentially. It doesn't let them out, as opposed to externally rectifying. So that's the GABA-B receptor. It's wildly distinct in function from the GABA-A receptor. The main takeaway is that the GABA-A receptor is ionotropic and it's ligand gated. And then GABA-B is a metabotropic receptor, which indirectly through G protein coupled signaling, intracellular signaling, causes stabilization of the internal membrane potential. So now that we got that out of the way, let's go on to the alpha-2 delta containing VDCCs. Now these are the actual targeted gabapentinoids. With the alpha-2 delta containing VDCCs, first of all, VDCC means voltage dependent calcium channel. It's also called VGCC, voltage gated calcium channel. And the reason it's called that is because, like NMDA receptors, they open when the associated neuron is sufficiently depolarized. So it's required that the associated neuron already has a degree of depolarization. So they're voltage dependent in that sense, that they are conditional and require that, and then they help facilitate the propagation of the action potential, kind of similar to an NMDA receptor. However, certain VDCCs contain what's called an alpha-2 delta subunit. And not all of them, but some do. And this is the target of the gabapentinoids. What this subunit or the subunit complex does, well, first of all, to explain the structure of this receptor, we have the alpha subunit here, which consists of the ion channel pore. There's also a beta subunit that I didn't illustrate that's primarily intracellular and then helps communicate with the alpha-1 subunit. Then we have the alpha-2 subunit, which is connected to the alpha-1 subunit and also connected to the delta subunit, which is a transmembrane subunit, while the alpha-2 is a extracellular subunit. So what happens is when you have a gabapentinoid bind to this subunit complex, it dampens and decreases the ability for this channel to transmit ions. In this case, calcium ions, divalent calcium ions. So it's indirectly inhibitory in the sense that it causes, so the purpose of this subunit here is to help increase the efficiency and the duration of the opening of this subunit. The alpha-2 delta is like a regulatory or modulatory subunit for the alpha-1 subunit pore. So when you have something bound on the alpha-2 delta subunit, like let's say gabapentin, it reduces the ability of this subunit to help positively modulate this subunit. And these receptors are found in various regions of the brain, and what this results in is anticonvulsant effects and alleviation of neuropathic pain is what gabapentin and pregabalin are sometimes prescribed for. I believe this also has anxiolytic effects, less so than GABA receptor ligands, but it's an inhibitory mechanism. It reduces the chance that the associated neuron will fire because it reduces the chance that calcium can obtain clearance into the cell, into the neuron. Yeah, so I think that's about it. I just wanted to briefly explain the difference between the gabapentinoids and the GABA ligands and maybe alleviate some confusion there, because I've seen a lot of people confused regarding the topic. So I hope this is a helpful explanation.